I welcome everyone to the mini course organized by Indian Women and Mathematics. This is the second mini course in this year. So today we have Professor Manjunath Krishnapur, who will be delivering a course, mini course on Markov Chains. So there are many other activities done by Indian Women and Mathematics, that is IWM, and I will request Professor Vidisha to tell a little bit about IWM activities and IWM itself.
Good morning, everybody, and it's a pleasure and an honor to have Professor Manjunath Krishnapur giving our second mini course on Markov chains. The Indian Women in Mathematics, known as IWM, is funded by NBHM and supported by Committee for Women in Mathematics, International Mathematical Union. We have many activities. Many of you may have visited our website, which is iwm.org.in. We have one annual conference in summer. Next year, it's proposed to be in IIT Patna. This year, we had it in WITS, Goa. Then we have a regional workshop which took place in October in Central University, Tamil Nadu, and next year it is proposed in IIT Kanpur. We have all these mini courses which are online. The other activities are offline. There is also a winter school this year in Vallabh Vidyanagar, Sardar Patel University in December, which is for second year undergraduate students, and all other activities are for PhD students and above, and some are for the master's students. And we also have May 12 initiative, which is supported by Committee for Women in Mathematics, and those take place under the umbrella of their own website, and we just coordinate them in India. Our main aim is to promote and encourage women to take up a career in mathematics, and mini courses are attended by people from all over the world, and this is one way of reaching out to a wider community. Our activities are not just restricted to women. Anybody, regardless of their gender, can register and attend these activities. And we will have 2 more mini courses, so watch out the space on our website for further detail for this. And this mini course is for today and tomorrow on Markov chains. Our activities are coordinated by many people. We have a 14-member EC, Executive Committee of IWM, and we also have people who help us, like Abhay here, and many other people where the activities happen, and I'm thankful to all of them. Thank you very much, and I hand over to Abhay again.
Okay, thank you very much. Now I request Archana to say something about the speaker and chair the talk.
Archana, you're muted.
Yeah. Good morning, everyone. We are truly honored to welcome Professor Manjunath Krishnapur, our distinguished speaker for today. Professor Krishnapur's academic journey is truly inspiring. He began his studies in the prestigious Indian Statistical Institute, which laid the foundation of his remarkable career. He then pursued his doctoral degree at the University of California, Berkeley, and further honed his skill as a postdoctoral fellow at the University of Toronto. Since 2013, he has been a valued faculty member at the Indian Institute of Science, Bangalore. His research interest lies in the fascinating field of probability theory, with a particularly focus on random matrix theory and the zeros of random analytic functions. His groundbreaking work has been recognized globally, as evident from his publication in prestigious journals like the Annals of Mathematics and Annals of Probability. He has had the privilege of collaborating with world-renowned researchers such as Yuan Perez, Terence Tao, Siddharth Gadgil, and many others. Beyond his academic achievement, he has been also authored the influential book Zeros of Gaussian Analytic Functions and Determinantal Point Processes, published by American Mathematical Society. Professor Krishnapur is not only a brilliant researcher, but also an exceptional educator. His website is a treasure trove of valuable lecture notes and engaging lectures. These includes both technical and popular lectures and are available for public consumption. We highly recommended watching these lectures to gain deeper insight into his work. We are incredibly fortunate to have a Professor Krishnapur share his expertise with us today through his insightful IWM mini course on Markov Chains. I just want to add to maintain dignity and decorum at all the time. Please do not post anything which is not related to lecture. In case you have any question, please post in chat box or in the questions. We will take up all questions at the end of the lecture. Without further ado, I hand over the proceeding to Professor Manjunath. I thank you very much for agreeing to lecture and looking forward to your lecture. Thank you.
Thank you, Archana. It's a great pleasure. Thank you, Archana, for organizing and also for inviting me to this. I've attended IWM offline, so it's the first time I'm giving a course. Yeah, so of course, it's a great pleasure. So I usually, none of my classes have this many audience, so I should be very excited. So, but on the other hand, the flip side is I really don't know my audience. So what I have pitched for, I don't know whether it will be exactly suitable for you or not. So if there are questions, so some questions can wait for the end, but some questions may be something, if not clear, if I don't mind being interrupted and asked. So one of the coordinators can do that if there are such questions which need immediate clarification. So as I said, I don't know the audience exactly. So I pitched it at, so Markov chains are both, it's a very nice piece of mathematics. Also, there are applications. So I don't know how far we'll get. So the idea is to convey some of this, okay? So let me start with, so this is a subject. So what we'll cover basics of the subject, really, basic theory of Markov chains. In the end, I will touch upon some later things that people have done more recently. So this Markov chains is about 125 years old now. It was started by Markov. So there are many Markovs. So this is A Markov. He started. So one of the motivations, so he had two motivations. One of them I'll come to later, but one of them was to understand text. Okay, so what is text? Text is like any you take a novel, you take so he was particularly looking at Russian novel of some novel of Pushkin or something like that. So what is a text like? Text is a string of characters. So we can, for simplicity, say they're a sequence of letters. So how to mathematically model a text, a piece of text? So if you take a piece of text, so for some purposes, it's written by an author, but for sometimes people may regard it as like, so it is just a sequence of letters, one after another. And maybe there are letters and let's say space. So letters and space occurring one after another in some fashion. And a moderately reasonable mathematical model could be, okay, so somehow these letters are picked up random and stringed together one after another. Okay, so whether that's a good model or not is a question. Okay, so let me show you a simulation. So I hope this is visible. So this is on Mathematica. I have pre-written so that we can do it more quickly. So here is, this is visible, right, Archana?
Yes, sir, it is visible.
Yes. Yeah.
Okay. So I'll not go over the whole code, but this is on Mathematica. I have written a code. So there is a data set of Alice in Wonderland, which has 49,217 characters. I have cleaned it up a little bit by replacing all spaces, and all the punctuations have been removed. Only just lowercase, uppercase have all been converted to lowercase. So it's a text. It has only characters, 26 letters, and space. Okay, so that is X. So I will not type out X, it's too long. So that is there. So the idea is whether we can, so this is for me not the actual text. This is like we think of this as the database. So your database may be the entire collection of all books in the world, for example. For simplicity, we have taken just one book here and one this text as our database. So based on this, what one can do is one can calculate the character counts, for example. So, for example, here CH is the characters of X. So all the character counts. So if I show for you, so okay, so this is a bit small in size, but I hope you see here character counts of X gives you how many of each letter comes here. So for example, this space has occurred 9,969 times, E occurs 5,000 times, T occurs 3,800 times, etc., etc. So this is the number of character count. So one model of language is that maybe you take these frequencies as E is more frequent than T, which is more frequent than A, and so on. So maybe you pick up letters with this randomly from this text and string it together. Does it look like text? So let's do that first. So here, when K is 1, yeah, so let me do this here. So what is this? I'm running a code here. So it will, maybe I should decrease the size. For some reason it's taking long. Okay. So what I did here is is this visible? I mean, so this is becoming very small for some reason.
It is
And so,
visible currently, yeah.
Okay.
That there you can.
So this sentence that you see here, ENEOE, this sentence is just a random sentence made up like this from the text Alice in Wonderland. I picked up letters according to the frequencies in which they occur, which I showed earlier. So E occurs with higher frequency than this and so on. So just string together the letters. And as you can see, it doesn't look like anything. It looks like garbage. Okay. Then, so this is how, this is like throwing dice independently. So each die will tell you which letter to put next. First comes C, then N, then E, then O, then E, then space, then T, and so on. So Markov had the idea that, okay, this doesn't look anything like text. Okay, this is not exactly what he did, but I'll pretend that this is what he did. So you can increase the memory of the text. So we know that text doesn't look like this. For example, Q will be followed by a U and so on. So what you can do is, so K equal to 2, I change K equal to 2. What that means is that it keeps track of what is the previous letter. Okay. Instead of looking at character, so here, let me show you what that is. Character counts of X comma 2. What it shows you is all the pairwise. So this is, for example, OW. O and O followed by W occurs 214 times. W followed by N occurs 61 times, and so on. Okay. So I use this data instead of just using the frequencies of individual letters to decide which one to come next. So when a T, first letter happens to be T here, and then what we do is, okay, it's for some reason. Okay, I hope it is clear. So T, when the letter T comes, what you do is you go back to this character counts and see how many, all the times T was followed by other letters. And you pick the one, T is sometimes followed by A, sometimes followed by E, sometimes followed by H, and so on. You pick the next letter with keeping in mind what was the previous letter with probability proportional to that. I hope it's clear what it means. I will explain later. So then if you keep a memory of one letter, then you get a new sentence which looks like this. It also looks like garbage. slightly less garbage than before. Then you can keep track of the previous 2 letters. Okay, instead of throwing dice independently, what you do now is you keep track of the previous 2 letters, and based on that, you see how many times. So let's see what the result will be. So here, so when N comes, so N and O. So to decide the next letter, what you keep track is N and O. You see how many times N followed by O occurs in the text Alice in Wonderland. And sometimes N followed by O is followed by T. Sometimes it's followed by I. Sometimes it's followed by L. So you keep track of the frequencies with which it is followed by various letters and put the next letter according to that frequency. And you see that this sentence starts looking a little more like the words, the sentence doesn't mean anything, but the words start looking more sensible. And if you keep longer memory, you start getting more sensible things. So when K is 4, we are keeping track of the previous 3 letters to decide what the next letter is going to be. Okay. So you see that you get a new sentence which starts looking a bit more like real words. The sentence doesn't look like a sentence, but the words start looking like words. You can see many of the words are actually meaningful, and the other ones look like they could have been words. CRTANT. It's not a word, I believe, but it looks like darling. Might be a word. It's not. So this is how Markov started the idea of Markov chains. So till then, till Markov, there was no idea of this kind of an idea of what follows being dependent on something before. Okay, so probabilists had studied, or people studying probability, gambling, etc., had studied throwing dice, etc., tossing coins, etc., where you throw a die and the next time you throw the die, it doesn't remember anything of the past. But this is something which remembers the past. That is the idea of Markov chain. So now that's the sort of motivation. So now let me start by defining what a Markov chain is. Okay, so what is this Markov chain? So instead of alphabets in a letter, we could have any other thing. Okay, so how is the definition made? So let me make a definition. I will give lots of examples, hopefully. So the definition of a Markov chain. Okay. So what is a Markov chain? Okay. So I'm writing the definition. So Markov chain starts with 2 ingredients. Okay. So we have to have 2 ingredients. One is S. It is just a finite set. So you can think of it as 1, 2, 3, 4 up to some n. So this is called state space. In what I was discussing with language, what is the finite set? It is the set of all letters, 26 letters and space. So there are n is 27. So there are 27 characters, and that is the state space. And then we have to give. So there are 2 ingredients. Ingredient 1 is this. Ingredient 2 is a matrix P. It is an S cross S matrix, or if you want, it is n cross n. If S has n elements, you can think of it as an n cross n elements, whose elements we denote by small p I comma j, I and j coming from your set. You order the set in some way, 1 to n, and you form this matrix. Okay, so this is the matrix P 1 1 up to P 1 comma n and so on. The last row is P n comma 1 dot 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 P n comma n. Okay. So this is called transition matrix. Okay, I have not yet said what these PIJs are. So the condition is this: these PIJs have to be not just any matrix of numbers, they have to be non-negative numbers. Okay. And all the row sums, so if I add the first row, the row sum should be 1. And row sum of each row sum should be 1. So that means that if I take Pi comma j, I sum over j in S, I should get 1. And this should happen for all I. So the row sums of this matrix are 1. So such a thing is called a stochastic matrix. It is so these conditions, any matrix with these conditions, non-negative entries with row sums equal to 1 is called a stochastic matrix. So in the context of Markov chains, we'll also call the transition matrix, because it will tell us how the strings of elements of S are produced. So these are the two ingredients of a Markov chain. And then what is a Markov chain? A Markov chain is, maybe this is just the, now I start the definition of Markov chain. So we have a sequence of random variables, x0, x1, x2, ... It's a sequence of random variables. S-valued random variables. Okay, I don't know why this is, okay, random variables. What that means is that each x0, x1, etc., they take values in this. So x0 is one of these values, but which value is random? Okay, so some coin is, I mean, somehow some random choices are made to decide what are x0, x1, but all of them will be elements of this S. But when you do the experiment again, you may get a different one. So a Markov chain is a very specific kind of sequence of random variables. It's called a Markov chain. I will just write Markov chain if the following is true. Doesn't matter what has happened so far. Okay. So when they are random variables, we have to tell what are the probabilities that, for example, what's the probability x7 is 1 or 2 or 3 or up to n. So the definition is that if you take x, suppose I tell you that the string so far is built up is this one. x0 is some I0, x1 is equal to some I1, and so on up to, let's say, xt is some I sub t. Okay, so let's say that I have shown you what the string developed so far is, like in the text. You have a string developed so far. Now what is going to be the next character? xt plus 1. What is the probability that it takes the value some j? Okay, so the thing is, for this probability should not depend on anything except this last one. That's what it says. So this is p I comma j, okay, where I is just I sub t. Okay, I could have written I sub t. So you look at, given everything that has happened so far, you look at where the last location is. This is this I, or I sub t. Then you look at the matrix, ith row of the matrix. So the ith row of a matrix will have pi1, pi2, pin, which add up to 1. So now you pick up 1 with probability pi1. So xt plus 1, next character will be 1 with probability pi1, 2 with probability pi2, and so on up to n with probability pin. Okay, so this is what a Markov chain is. It's exactly like I showed you in the text business, where given the string up to now, based on what is the previous letter, we tell what is the next letter. Okay, so this is only memory 1. You might why, okay, why then I extended it further, keeping track of 2 letters, 3 letters, etc. Turns out mathematically we don't need to do all that. If we do this, we can cover all of those things. So this is the definition of a Markov chain. So given, so there are 2 ingredients, a finite set, state space, and a transition matrix, which is a stochastic matrix. And once that happens, this is how you do. This is how you get, I mean, a sequence of random variables is called a Markov chain if this is what happens. So you start with some I0, then pick the next one according to the row defined by I0. That gives you a probability vector, and you pick the next letter and so on. So this is the definition of Markov chain. So we will discuss many examples. So it's one of the good things is to discuss examples. There are many things which are many examples. So maybe I discuss a few examples which will make it clear. So the simplest non-trivial chain would be to take just a two-state Markov chain. Okay, so let's call it two-state Markov chain. So what will it have? So the states, there are only two states. You can call them 0 and 1 or 1 and 2, whatever. Okay, I call them 0 and 1. And then P will be a matrix. It has to be a 2 by 2 matrix. What is the properties? The entries have to be non-negative and they have to add up to 1. So suppose I put alpha here. Since this must add up to 1, this must be 1 minus alpha. And if I put beta here, this must be 1 minus beta. And all of them have to be non-negative. So alpha and beta are between 0 and 1. So you fix alpha and beta in 0 and 1, then we get a certain stochastic matrix. It could be half, 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 or 1, 3/4, 1/4, half and half, anything. So any such choice gives us a transition matrix, and the transition matrix defines a Markov chain. Now this Markov chain, a good way to indicate it graphically is like this. So instead of writing this equation, one way for small states we can do that. So there are two states, 0 and 1. What is this telling us? So if the current state is 0, so if you look at this defining property of the defining property of the Markov chain, so given the current state, all that happened previously don't matter. Given the current state is I, it will be next will be J with probability Pij. That is the defining property of Markov chain. So here, if the current state is I, what is the probability? Next state will be J. So here, the two states I have written correspond to, actually, this is, I should say what corresponds to what. This is for state 0, this is for state 1, this is for state 0, this is for state 1. So that means if you are at 0, you go to 1 with a probability alpha. Okay, and you stay at 0 with a probability of 1 minus alpha. And if you are at 1, you go to 0 with a probability of beta, and that is coming from the second row, and you stay at 1 with a probability of 1 minus beta. Okay, this is how so each time you just toss a coin independently of everything that happened before to decide what is the next letter. If you're at 0, it could be next maybe 0 or 1. Again, you toss again and 0 or 1. And if you come to 1, you toss a different kind of coin to decide what is next. So this is the simplest Markov chain. Nothing interesting, but it will be a good thing to work with. We will work out things in this two-state Markov chain before we go to anything else. So let's come to a slightly more interesting example, random walk on a graph. Okay, what is a graph? I will just write picture. I have a simulation I will show you also. So a graph is, so we have finite set of vertices like this, connected, some of them, there is edges between some of them. Maybe like this. Okay, so these are the graph has a vertex set and an edge set. The vertex set is, what are these nodes? 1, 2, 3, 4, and 5. In this particular graph, I have 5 nodes and there are a bunch of edges. 1 and 4, 1 to 4 is an edge, or 4 to 1. 1 and 4 are connected, 3 and 4 are connected, 4 and 5 are connected, and so on. So the idea will be that the description of this random walk is that wherever you are, go to one of the neighbors with equal probability. Neighbors means adjacent vertices. Adjacent vertices with equal probability. Okay, so that is the verbal description of what simple random walk is. And that actually is specifying. So in other words, the state space is actually, so what is it in terms of Markov chains? The state space is the state space here is the vertex set. And what is the transition probabilities? So I have to tell you what is the, if I am at vertex I, what's the probability? Next I will be at vertex j. What it is telling is, this description is telling you that, for example, if I am now at 1, next I may be at 2 or 3 or 4. It's not directly connected to 5, so it cannot go to 5. It has to go to 2 or 3 or 4. And what are the probabilities with which it goes? 1/3, 1/3, and 1/3. But if you are at 2, you can only go to 1 or 3, and you go with probability half and half. If you are at 5, you can only go to 4, so you go there with probability 1. So in general, Pij will be what is called 1 over the degree of j, degree of I, sorry. So what is degree of I? Degree of I is the number of edges at vertex I. Okay, so for example, degree of 1 is 3, degree of 3 is also 3, degree of 4 is 3, degree of 5 is 1, only one edge, degree of 2 is 2, and so on. So you go to j with probability 1 over degree of I if j is adjacent to I. So we write like this, j is adjacent to I, otherwise you cannot go there, so probability is 0. If j is not adjacent to I, you cannot jump directly from I to j. You may go after many steps, but you cannot go there in one step. So let me show a simulation here. So of a simple random walk.
Professor Manjunath, there is a question in
Yes.
YouTube related to the definition. Shall we take it?
Sorry? Yeah.
So Urmisha Chatterjee is asking, is Pij the older state and J the new state? She's having difficulty understanding the conditional probability in terms of the transition matrix.
Right. So always when I write P I comma j, I is the vertex where we are. The second one is the vertex where we are going. This is the, if I am at state I, Pij means, okay, so Pij is the, so look at the definition here. Pi comma j is the probability that, so there is a lot in this one. So for a moment, forget all this x0 to xt minus 1. So what it is telling you is that if the current state xt is I, so sorry, I and it are the same here. If the current state is I, then next time you will be at j with probability Pij. Okay. And this is saying more. In fact, even if you know all how you came up to here, it doesn't matter. Only the current state matters to determine what probabilities you will go. I hope this clarifies. Is it okay?
I hope so.
Okay. So let me show, maybe it will help if I, so we'll see here. So let me go to the simulation. So here is, okay. What is this? Okay. What is this G? Okay. So here I make a, okay. So I ran some code. It doesn't matter. So let's run, I see this picture. So in this picture, I'm going to run this now. Okay, it's actually running. Okay. There was some older running simulations. Well, let's see what comes. So what I have done here is I make a graph with 6 vertices and 11 edges. Okay, I just made some graph with 6 vertices and 11 edges. And what I'm going to show is random walk on that graph. That's all. Maybe that picture will help, but it's taking enormous time for some reason. It used to do it very fast. Okay. Okay, maybe I go back to this one. I'll come back to this and show. Once the simulation is complete, I can show. So here, the point is if you're at vertex 1, you will pick one of these vertices, go there. And then if you come to 4, then you will pick one of 1, 3, or 5 with equal probability. Go, let's say you come to 5. Then you have to pick 4, next step. You come to 4, and you come to 3 or 1, and so on. So it keeps going like that. So that's what random walk on a graph is. So when the simulation is complete, I will show that. Okay, maybe let me check that. Okay, it's for some reason it's it's not working. Okay, it may.
So there is another question.
Yes.
Uh,
Yeah, please.
Why is it required to bring a new coin when one reach at state 1? Does it happen for state 0 also?
Say it again. I didn't catch.
Why is it required to bring a new coin when one reach at state 1? Does it happen for state 0 also? I think
There is no in
previous
in the previous one.
previous
Okay.
one.
So what is the question? So state 1. So you can go back to the same state also. It is possible. So we don't. So here I'm not saying J should be a different state from where I am. I may decide to stay where I am. Okay. So for example, if you're at state 0, you may decide next moment also. So T for me will be always a discrete variable denoting time. So if at this time T I am at state 0, next time I am allowed to be at state 0, or I may leave state 0 also. So here in this chain, it is going from 0. If you are at 0, it will go to 1 with probability alpha, and it will stay there with probability 1 minus alpha. If you are at state 1, it will go to 0 with probability beta and stay at 1 with probability 1 minus beta. If you don't want it to stay, then it's simple. Then it will go alpha, make it 1. Then it will not stay at 0. It will go to 1 with probability 1. And make beta also 1. Then it will come back to 0. It's a Boeing chain. From 0, it will go to 1, will come back to 0, will go back to 1, and so on. So in general, it is allowed to stay in the same state. That is allowed. Okay, so there is a problem here. This, okay, so this I'll have to do later. But okay, so let me explain the other examples. Maybe in the beginning of next lecture, I'll show the simulation. Okay, so then third example, it's a very important example historically, and it's a very beautiful example also. Here, it is called a Hagenfest chain. So Hagenfest was a physicist. So this is a very important, historically very important object in statistical physics. So here, the state space, I'm writing it graphically to indicate. So is like this. So there are states are running from 0, 1, 2, 3, ... up to n. Okay. So this is actually coming from the following model for gas. So n is a very large number. So there is a chamber. You can think of a chamber where there is a partition with a small hole. Okay? And there are gas molecules on the left. There are gas molecules on the right. So the idea is that at each time, we think of time as 1, 2, 3, 4, etc. At this time, suppose the gas is like this. What happens is one of the particles, so there are a total of n gas molecules. 3 of them are on the left, and here there are 7 of them on the right in my picture. So one of the 7 gas molecules is picked at random, and it will be moved to the opposite side. Okay, if this molecule is picked, then next time you will have 4 in this side and 6 on that side. Or if something here is picked, there will be only 2 on this side and 8 on the other side. So that is the idea. So the verbal description is pick one of n molecules at random and move it to the other side. Okay, so move it to the other side. Now, in this picture, this refers the other side. It refers to this picture with a box with a partition with a hole. Okay, so this is the idea, and it keeps happening. So, what is the state of the system? State of the system, we don't really care. Molecules are all identical. What we care about is the number of. So why did I write this graph? Let me say. So let xt be the number of molecules at time t in the left partition, in the left half. So how many particles? So at this time, there are 3. So if this is time is t, xt is 3. Next time, xt may become 4 or it may become 2. Okay. So what is the transition? So what are the values of xt then? The state space will be, so the number of molecules here can be 0, 1, 2, 3 up to n. So that's why I wrote that graphical picture 0, 1. The state of the system is just how many particles are on the left partition, and that is 0, 1, 2 up to n. And what is the transition probabilities? Okay, so pi, suppose we are at time t, we are at I. That means there are I molecules on the left. Next time, what will be the number of molecules? What is the probability that the number of molecules is j? Okay, so the idea is like this. It can only be I or j can be only I minus 1 or I plus 1. J is I minus 1 or j is I plus 1. But if not, if j is not I plus or minus 1, then the probability is 0. Okay, so at each time instant, only one change will happen. Either one, it will decrease or increase. Now, what is the chance that it will decrease? So suppose there are I particles here. Then there are n minus I particles on the other side, and I pick one of them at random and move it to the other side. So for the number of molecules here to decrease, I must pick one of these I, right? If I pick from the other side, that will come this side and it will become I plus 1. If I pick one of these, it will go to the other side and it will become I minus 1. So what's the probability that it will decrease is I divided by n. And what's the probability it will increase? It will be n minus I divided by n. Because one molecule is picked at random and moved to the other side. If the picked molecule is on your side, on the left side, then it will decrease. If the picked molecule is on the right side, then the number of particles on the left will increase. So this is the Markov chain. So in this graphical way, we can write. So if I were to write, so 0, 1, 2, 3, like this. So from 0, what happens? From 0, if there are no particles here, particle will be picked on the other side. So it will surely go to here with probability 1. But when you have one particle on the left, you will go to the other side with probability n minus 1 by n. Or you may go back to 0, means if this particle is picked, then it will go to the other side and left side will become empty. So when you have two particles on the left, with probability n minus 2 by n, you go to the 3, and with probability 2 over n, you go to 1. So this same, what I have written here in formulas, I have written here in graphical way. That's all. 3 by n, n minus 3 by n, and so on. Towards the end, we have n minus 1 and n. When you are at n, you can only go to the left. If all the particles are on the left side, you can only decrease. This happens with probability 1. Whereas from n minus 1, it decreases with probability n minus 1 by n and increases with probability 1 by n. So this graphical way of writing is the same as this formula. Okay. If you write the transition matrix, it will be a very sparse matrix, which has mostly zeros. It will be 1, 0, 0. If you write it as a matrix, then it will be 1 by n, 0, n minus 1 by n, 2 by n, 0, n minus 2 by n, and so on. So it will be a tridiagonal matrix. The only non-zero entries are on this diagonal and this diagonal, not on the main diagonal, but the one above and below. Okay. So this is the Ehrenfest chain for this. So it is supposed to represent gas molecules. So for example, you are sitting in a room. So one question is, so is there a chance that all the gas molecules will move to the other side and you will suffocate? So far, it has not happened. Otherwise, you wouldn't be attending this lecture. So what is the chance that it will happen in your lifetime? Could it happen that all the molecules will move to the other side? How many steps will it take? So we will later, when we analyze, we will see this. So it was important to clarify certain matters in statistical physics. Okay. So then there are many other examples. So let me give more examples. So examples are really heart of the subject. I mean, so what we will do later, but so have some examples. Always keep some examples in mind. Okay, so card shuffling.
Sir, there is one question
Yeah,
related to the earlier example.
sure. Yes. Which one?
Huh. So Parnakar is asking, this example, it seems like if we simulate this a large number of times, eventually there will be an equal number of molecules in both chambers. Is that correct?
It can happen. Yes, it will reach that, but it won't stop there. Even after that, the dynamics will continue. Even if there are equal number, you will again pick one of the molecules. Let's say there are 10 on this side and 10 on that side. With probability half, you will pick on this side or on that side, and it will become 9 and 11 or 11 and 9. So it will never stop. It will keep moving. But it's good. I mean, that's a question. So I asked, will it sometime become 0 on this side? You can ask, will it sometime become equal? Or will all the molecules become n on this side? So that's a very interesting question. And the answer is yes. We will see later, hopefully. Okay. So far I'm only giving example of the chain. I'm not actually doing anything with it yet. That what are the questions to ask about Markov chains also I have not yet said. So okay. So at the moment we are only giving examples. In fact, we stop at 11:30, right? So maybe this lecture I will only finish with examples. Next lecture I will start with what questions are there about Markov chains that we are interested in. I will focus on a single most important question of Markov chains, and we will hopefully completely prove it. Okay, but let's continue with examples for now. What is card shuffling? So you may have seen card shuffling algorithm. So what card shuffling is what? I mean, when you play some card games, what you do is before you commence a game, you take this deck of cards, okay, and you shuffle them in some way. There are many ways of shuffling. So what you have is, so here you will have a deck of cards. A deck of cards looks like something like this. Often it's 52 cards. Okay, so there may be 52 cards, and the shuffling is something that does to change the order of the cards. Okay, so the interesting ways in which you shuffle, maybe you will pick up, I mean, there are many complicated ways of shuffling. One is you pick up some bunch of cards and put them to the bottom, or you pick up some set of cards. So one kind of shuffling where you pick up some bunch of cards and move them to the top. Okay, so that's kind of a shuffling that mechanism. But to keep things very simple, although not very realistic, let's start with all these shuffling mechanisms are actually Markov chains. Actually, that's what I want to convey here. Any card shuffling, any method of card shuffling defines a Markov chain on what? On the set of permutations. So here, what is the state of the deck? The state of the deck, maybe the third card is at the top, first card is here, seventh card is here, 22nd card is here, 51st card is here, and so on, right? So what we have, the state of the deck is a permutation. So my state space here is Sn. It is the set of all permutations on or the set 1, 2 up to n. So a deck of cards is an order. Okay, the cards, which cards are there, we know. That's not in question. But what is the order in which they are? That is the question. And there are, if n is 52, so n is the number of cards. Example 52. So this state space is enormous. The things that I showed you was like earlier, I didn't say what n is here, but this had only 5 states. But now we are coming to a state space which has 52 factorial states, enormous. Now each card shuffling mechanism, so a simple shuffling mechanism is so those realistic shuffling mechanisms will take time for me to define and so on. So let's not complicate our lives. This is not a realistic shuffling mechanism. A simple shuffling mechanism is pick two distinct cards and interchange them. Their positions. Okay, so this is the verbal description. We will have to write what it means in terms of the transition matrix. So for example, maybe I pick two cards, maybe that turns out to be 1 and 22. Then we are going to move 22 there and 1 here. We will interchange the two cards. So that is one move. Okay, now you have a new arrangement. You pick two randomly cards. So pick two distinct cards at random, I should say. Pick two distinct cards at random and interchange their position. And you keep doing that. This will take such a long time to,
This n should be n factorial, is it?
Okay, so this n, okay, sorry. Okay, so maybe to keep the...
It is 52 factorial, I just wanted to check because...
Right. Sorry. So let me, you're right, because it conflicts with my earlier. I always was using n for the size of the state space. So let us say the number of cards is k. Okay. So then this is S sub k. K is the number of cards, but the cardinality of S, how many elements are in S? That is k factorial. So this is n. The number of states is k factorial, which is 52 factorial. Number of cards is 52. Okay. So I will keep n for the number of states in the system. And so k is, let's say, the number of cards. Okay. Okay, so then what is the shuffling mechanism? How do we write this? So here, what is the transition matrix? Transition matrix has 52 factorial rows and 52 factorial columns. It's a square matrix with 52 factorial. We are not going to be able to write it like that. So we have to just tell what are the entries. So the entries, the transition matrix, so this is a Markov chain on S, K with transition probabilities or transition matrix given by. So if we are currently at some permutation pi, what is the chance that next moment I will be at a permutation sigma? So fix a pi and sigma are permutations. Okay. So p pi comma sigma means the probability if current arrangement is pi, what is the chance that after one move the arrangement will be sigma? So what is this probability? Okay. So, well, okay, I usually like to ask questions and take answers, but I don't know how to do it here. So in this case, so whatever be the arrangement, how many arrangements can it move to? So we have to pick two cards out of this k of them. So there are k choose two ways of picking two cards. Okay. So I could pick the top card and the bottom card, or first card and 7th card, or 10th card and 25th card, whatever. So there are k choose two ways of picking. So this probability will be k choose two, but not for every sigma. So for example, if you imagine the arrangement 1, 2, 3, 4, 5, suppose the original arrangement was this. There is no way that after the first move, I will go to this arrangement, right? Why is it not possible? In this move, in one move, only the state of two cards will change, not more than two. So here, this is not possible at all. Okay, this is not possible in one step. So the only sigma to which you can go are those that you can get from pi by multiplying a transposition. Tau is a transposition. So transposition means it is a permutation that interchanges two things, some L and some M. Okay, so this means this is a permutation which interchanges L and M. All the others stay the same. L and M are interchanged. L is in position M, M is in position L. So permutations can be multiplied. So this is this and 0 otherwise. So this is random transposition. This is one shuffling mechanism. Okay, this is just one shuffling mechanism. There are other shuffling mechanisms. So I hope this is clear. I will give one more shuffling mechanism. maybe I will write it in the next. If there are any questions about this, I can take that also. Okay, so I hope this is one shuffling mechanism. I'll tell you, this was boring enough, but I'll tell you an even more boring shuffling mechanism. So this one we call settling library. Okay, there's a different interpretation of this. Here, it's like the same as above. S is SK as above. But what we do is the shuffling mechanism is different. Shuffling mechanism is pick a card at random and move it to the top. So earlier we were picking two cards and interchanging them. Here you pick one card and move it to the top. That is the shuffling mechanism. Okay. So I will not try to write the P here. I hope because it's also close to time. So, but I just want to, I hope you will be able to write this. But this is a very simple one where if you have a deck of cards, what you do is, okay, so here I'll say in terms of deck of cards. So you pick one of the cards at random. If you pick this one, then this will come to the top. So for example, let's say original arrangement was 1, 2, 3, 4, 5. And you pick this one. So what will be? So this is x1, x0 times 0. This shuffling, this arrangement is x0. What is x1? After, if you pick this, then 4 will come to the top. And the rest of the cards will just go below 2, 3, 5. Now what you do is you pick again one of these at random. So maybe you pick 2. If this is picked, then x2 will be a different arrangement where 2 will come to the top, then 4, then 1, then 3, then 5. Okay, so the cards will be in a new arrangement and so on. This is the Markov chain. This is how the Markov chain progresses. Now, who would shuffle cards like this? Nobody. But this is called settling library. Maybe it is a bit more if you want, if you don't like this boring shuffling. There's a different one which maybe, if you are like me, it is a very identifiable situation. So you have a bookshelf with lot of books. So this is book 1. So book 2 and so on. Okay, or rather they are not necessarily arranged. So you have K books in a shelf. Okay, what you do is suddenly you feel motivated and you pick up one book at random. You either read or don't read, and then you are too lazy to put it back in its place. So it will come to the front of the thing and you will push everything backwards. So that's exactly the same shuffling. So instead of cards, you're thinking of books in a shelf. Originally, maybe you had arranged it nicely. You will pick one book at random, depending on your motivation. Then you put it at the front and then you push everything to the wall. And then tomorrow you pick another book and then it comes to the front and you push everything to the back. So this is a new mechanism of shuffling, which is called settling library. So there are many other examples, which I have not, maybe one more. Is it okay if I take 2 more minutes to say?
Yeah, sure, sir. You can go.
Okay. So one last example, which is not exactly
What will be P pi sigma? That will be 1 upon K times something, is it?
It will be 1 over K, but for only K different permutations.
Right.
I mean, it just takes, so yeah, you're right. So P pi sigma will be 1 by K if sigma is something. Okay, I will say what that something is, 0 otherwise. What is that sigma? Sigma should be got from pi by what transposition? A transposition that transposes the first card with some other card. 1 comma I for some I equals 1 to up to K. Okay. So this is a transposition. So like here I got LM means to interchange L and M. Here it means interchange the first card with the ith card. Now okay, there is a slight bad notation. This I can be 1 also, in which case you are picking the ith book and putting it at the front. It means you are not doing anything. That's also allowed. But you pick one I and this is only these transpositions are allowed. That's what it means. Exactly. Yeah. Okay. So I will take a minute to tell one more thing. This is just to say that my definition was limited. So there are many situations which are modeled by Markov chains. One of them is Q. So let's say you have a cafeteria where there is a coffee shop, and then there are people standing in a queue to get coffee. Okay. So at this time, 3 people are in a line. So in this case, what happens? How does the queue develop? Queue, what happens? Of course, that happens in continuous time, but here we think of in discrete time. So xt for me will be the number of people in queue at time t. So t will be always 0, 1, 2, 3, 4, and so on. Okay. And how does it change? So the only difference why I'm bringing this example is, so at each time instant, so let's say the rule is at each instant, either a new person joins, let's say this happens with probability, let us say the probability is alpha, okay? Or one person is served and leaves. So one person gets his or her coffee and leaves, let's say with probability beta. So one of the two things will happen. In every time instant, either it will decrease by 1 or increase by 1 with this probability. So what is the state space in this situation? What is the state space? This is why I just wanted to just rush through this example. This is not, I said state space is finite, but here the state space is not finite. The number of people in the queue can be 0, 1, 2, 3, but there is no limit on the number. Okay. So this is an infinite state space. This is just to say that when you go to a Markov chain class, usually Markov chains are defined as having state space which is finite or countable also. But because this is a short course, we don't have time for, we'll stick to finite state Markov chains, which are good enough. But this is an infinite one. And then the idea is that P, if you are at I, I plus 1 happens with probability alpha. Okay. Oh, sorry. I should have. Sorry. I should. I made a mistake. This probability should be 1 minus alpha, not some beta. So with probability alpha, one person adds on with probability 1 minus alpha. So Pij is alpha if j is I plus 1 increase, or 1 minus alpha if j is I minus 1 and 0 otherwise. This is for I greater than equal to 1. I greater than equal to 1. From 0, you cannot go down. That was kind of implicit, so we should say that separately. P01 will be 1, let us say. Or P0, okay, P0j, let us say, is alpha if j is 1. But it will not go to minus 1. When there are no people, it cannot go to 1. With probability 1 minus alpha, nobody comes. And so it stays there. And 0 otherwise. Okay, or graphically 0, 1, 2, 3, 4, these are the states. What you generally happens is you go up with probability alpha and down with probability 1 minus alpha. Same with from any state. From 3 you go to 2 with probability 1 minus alpha. Maybe I should write all the, yeah, it's okay. So 3 with, so it will go to the right with probability alpha. Only at 0, it will go up with probability alpha and it will stay there with probability 1 minus alpha. So this is a nice simple model for a cube, and you can ask whether the cube will blow up or whether it will stay, it will hit zero quickly, how long will it take to get served, etc. So, but this is a little outside of my setting. That's all I wanted to say. Okay, sorry, I went over time. I'll stop here. We'll resume in
There
the
are
next.
some questions. Will you take it?
Yeah. Very happy to take them.
So
Yeah.
YouTube, I'll just read one. What happens if there is more than one new arrival at the same time?
Okay, that becomes, it is possible to model such things. I mean, so for example, maybe at each time, either one person comes with, so you can just do that. That's not a problem. It's not, I mean, if you want, say, let's say you even have, let's say, one person comes with probability alpha, or two people come with probability beta, or nobody comes with, one person gets served with probability 1 minus alpha minus beta. Then you will have pi I plus 2 will be non-zero. What you are saying is it can go from I to I plus 2 in one step. That's okay. That's also a Markov chain. You can model it.
And there are these general questions. Yuba is asking, what is the requirement to bring a new? Okay, sir. That is, I think, yeah, sorry. What is
No,
the
it's okay. Any question is fine. Yeah.
What is the significance of these Markov chains? What problem does this solve exactly? That is a question by Mrunmai Kulkarni.
Okay. So this is okay. What problem does it solve? Okay. It is a firstly it is a new model to model many new phenomena. Okay. So you can that is what I was trying to say with the language situation, that many things in the world have to be modeled with randomness, like throwing a die, tossing a coin, etc. Now, there are many realistic things which have to be modeled with random things. But the simplest random things that we see in first probability course are keep throwing a die again and again, and each time you will get a new outcome with which is completely independent of everything that happened before. Okay, so that is okay for certain modeling certain things, but it is not okay for modeling certain things. For example, in the case of Q is an example of an interest. So there are many situations where there are queues, whether you are thinking of physical queues like this at a coffee place, or when you are trying to do something on the internet. Everything has to be like, a lot of people are trying to access some video, then who will get it? So there is a queue for that. So when you are trying to access a video, so there is a Markov chain there. There is a queue there also. So queue is a very important application of things, but it's not. So if the queue size is 3 now, in the next instant it won't be independent of it. It will be close to 3. It may go down a bit or go up a bit. So it has to be modeled as Markov chain. If you model it like the queue size today and queue size now and queue size next instant are completely independent of each other, that's unrealistic. So which is why this modeling is necessary. It increases the set of models. Okay, this increases the set of models, but we have to be able to do something mathematically about it. Otherwise, there is no point. That we will do in the next lectures.
Price of plane tickets, is that depends upon these kind of things? Because I mean, if many people are trying to book a ticket, is it that or some?
It need not be as simple as this. Markov is actually the simplest dependent model. So I said that throwing dice is independent. This is brings a slight independence, but it is not. It is an independence of a specific kind where the next state depends only on the current state, meaning the randomness of the next state depends only on the current state. Okay. So there are more complicated situations which may depend on a lot of things. Okay. So the way so it need not be Markovian. I mean, it could be sometimes. So in case of plane tickets, I do not know what exactly you want to model. How the price changes, for example, with time. Maybe it is Markovian. One has to check and see. When you ask whether one can propose a Markovian model and check whether it works or not. Ultimately, experiment will have to tell.
Riti, do you have some question? You raised the hand. You are mute.
Hi, Manjunath. It's
Hi.
a very lucid talk. I was wondering about your last example, where you put 0 to. Can you just push it?
This Q example.
The last one, yeah. So if it is 0, it can only go to 1 or remain 0. But why is this probability 1 minus alpha for j equal to 0?
When I wrote each instant, the arrival of a new person has probability alpha.
Yeah.
Okay, I mean, this is not the best model I could have described. Let's just say that it is 1 minus alpha. Okay, actually I could have made a more realistic model where both things can happen. A person can come, a person can leave, both can happen or neither can happen. That's also possible. These two should be kind of independent. That would be a better model. So here I just...
okay, you want it to be total 1. That's why you've written that.
So that's what I did. But
right.
the more realistic one would be that with probability alpha, a new person joins. With probability beta, a person is served.
Okay.
And then you will have to modify. Then, so if that happens, then it can happen that both. So if probability alpha for a new person and probability beta that a person gets served. Then what happens is you go from I to I plus 1 with probability alpha into 1 minus beta, because new person should come but nobody should leave.
Okay.
And you go to I minus 1 if with probability beta times 1 minus alpha. No person should come but 1. And it can go to I with certain probability and so on. That would be more nicer model.
Yeah, okay. Yeah, thank you.
Sure.
There are some more questions. Arka Roy is asking, does Markov chain has any relation with finite state automation?
Automaton, yeah. That's a very good question. So Markov chain, it is exactly a stochastic automaton, if you want. So what is automaton? So if people have never heard of automaton, don't worry. So it's a dynamical system, like Newton's laws. What does Newton's law say? You have a system of, let's say, bodies. So there are some bodies in space. If you know the positions and the velocities at this time, then you can calculate where they are going to be for all time in future. Okay, the differential equations of classical mechanics tell you, if you know the state of the system now, you can calculate the state of the system forever, where the state means positions and velocities of the particles at the given time. So a discrete situation of that is what is called an automaton. You have finitely many states, and it tells you if you are at this state, you will go to another state. And if you are at this state, you will go to this state. If you are at this state, you go to that state. And maybe if you are at this state, you go back, you go to this state, whatever. So that is what an automaton is. Markov chain is a stochastic automaton. It doesn't tell you where you will go. It tells you the probabilities with which you will go. You can go to multiple places. You don't know. But it tells you the probabilities with which you go to different places. It's exactly can be called a stochastic automaton.
There are some more questions, but if you want, we can take a break and we can take up those questions.
Yeah, I am looking at it in terms of Markov process. See, Markov process is I am reading it, so I'll quickly go over all of them maybe. I mean, people can leave also, that's okay, and come back. When do we meet again? So what is the time when we resume?
Just let me check, okay.
12 now.
12 o'clock. 12 o'clock.
12 o'clock. Okay. So I will go over these questions and tell anybody who wants to take a break can definitely take a break. Okay. So I am reading this question. Shall you define the Markov chain in terms of the Markov process? See, Markov process is something more complicated than Markov chain. We are not going to touch. So we are talking about finite state space, discrete time, stochastic process, a particular type of finite state space, discrete time stochastic process. Markov process is when you generalize this to continuous time and maybe continuous space. So that's more complicated. Okay. What is the real life application difference in using continuous time and discrete time Markov chain? Good point. Sometimes it's more convenient to formulate. Physicists will not care. Anything is okay. You can think of time as discretized or continuous. actually everything can be modeled in either way. Just mathematically, sometimes it's more convenient to do in continuous time and sometimes more convenient to do in discrete time. Here, the discrete time has the mathematical simplicity that you have only a sequence of random variables, one after another. Whereas continuous time would be more complicated. So it's best to just whichever works is fine. But for real life application, we can use discrete time or continuous time. It doesn't matter. For example, you think of like accessing a video, as I was saying, on a computer. You can think of it as continuous time, or you can discretize time to the level of 1 microsecond or something like that. That's probably okay. Okay. Can possible to any Markov chain can make a queuing model? No, I didn't understand this question. Queuing is one particular type of Markov chain. Not all Markov chains are that kind. So, for example, card shuffling is not a queuing model. Simple random walk on a graph is not a queuing model. Okay, in what sense is the infinite state space beyond the setting of current talk? If I'm right, yeah. So why I did this is that when I actually prove the theorems, I will assume finite state space. Definition I could have made with countable state space, no difference. But when I actually prove something about it, I will stick to finite state space because I have finitely many lectures. So that is the reason. Okay. So next question, is the transition matrix dependent on time? No, the way I defined it, it is not dependent on time. In example 6, I think it is dependent on time. No, nowhere is it dependent on time. What was example 6? No, it is never dependent on time. It depends on the transition probabilities depend on the state of the chain, not on the time. So here, for example, in problem 6, suppose there are 3 people, it will decrease to 2 or 4 with probabilities alpha and 1 minus alpha. And it doesn't matter what the time is, whether it is today or tomorrow, whether it is 12:30 or 1:45, the same transition probabilities are there. So it is not depending on time. It is possible to allow Markov chains transitions to depend on time, but it just complicates things. I mean, and we can say very little about it. So we stick to this. Okay. So I don't know if I'm actually answering questions. I'm pretending I'm answering questions. So next question, if I'm solving any stochastic differential equations, is there any role of Markov chains? Perhaps depends on which stochastic differential equation it is. Those are much more complicated matters than what I'm addressing here. Okay, so it's well outside of this one. Okay. What is the difference in solving methods for continuous time and discrete time MC? Yeah, so continuous time is technically more complicated. Discrete time is technically easier. That's why I'm sticking to discrete time. But in a full course in Markov chains, first people study discrete time Markov chain and then go to continuous time Markov chains. For example, if you take in ISI, so they have a 1 semester long course in Markov chains. Now we are trying to do 4 lectures. The bad way to do is to compress that semester into 4 lectures. Better is to leave out a lot of things and say some essential things. So that's what I am trying to do. Not try to say everything about Markov chains, but something about it. What is the significance of long-term behavior of Markov chain? I did not yet bring up this topic, but that is exactly what we are going to study. That will be the next lectures. To know what happens to we know how it develops one instant to next instant, but what happens globally over a long time? That is what we would like to know, and we will discuss this in the following lecture.
There is one question on YouTube. I think you have already answered. In example 6, state space is infinite. So how does the transition matrix look like? And what
so it is an infinite matrix. You can call it an infinite matrix. So the transition matrix has rows 1, 2, 0, 1, 2, 3, etc. Columns also 0, 1, 2, 3, etc. So it's an infinite matrix. So here, so if I take 2, 3, this will be P2, 3. That will be the entry in the second row, third column. So it's an infinite matrix. Most entries of it are 0. Okay, only a few entries are non-zero. But this is an infinite matrix. This is why, I mean, someone else asked why I stick to finite state space. You can call it a matrix, you can do anything, it's an array of numbers, but actually we are going to use matrix theory, we are going to use eigenvalues, eigenvectors, etc. to analyze Markov chains, to study the long-term behavior of Markov chains. And for infinite matrices, there is no such theory, which is why I'm sticking to finite state space. Other methods are used for infinite state space.